Okay, this is similar to number 12 in the chapter 4 review packet. This is a graph of f prime, the derivative of f, which is shown below. So y equals f prime of x. So one thing I could do is make a y, or an f prime number line chart. And the y coordinate tells you the derivative. So that means that the y coordinates here, would they be positive or negative? Positive, because you're going up. So you have a positive first derivative up until negative 3. At negative 3, there's no y coordinate, so it's the y coordinate's undefined, so f prime would be undefined. How about from 3 to 0? You go down, so is the y coordinate negative or positive? Negative. At 3, or at 0, there's no y coordinate, so f prime would be undefined. How about to the right of 0? Positive y coordinate, because you're going up. So let me see if I can sketch this graph a little bit here. It's going to have positive first derivative, which means the original graph of f of x, I'm going to try to sketch f of x, is going to be increasing. Now notice that the y coordinates start out close to 0, don't they? That means the slope on my original graph will start out close to 0. And the y coordinates get higher. That means the slope will get higher. So it'll increase. So the graph's going to increase, starting with a low slope, and then going to a higher, starting with a low derivative close to 0, and then going to a derivative that's a little bit higher. So it's going to go something like that. Then it's going to jump to a negative y coordinate, or to a negative derivative, which means the original graph of fx is going to have a negative slope all of a sudden. So what's going to happen right at 3? A corner, yep. And the slope's going to get more and more negative because the y coordinate's getting lower and lower. The y coordinate's going to negative infinity. That means this slope is going to have to go to negative infinity. Very, very steep. Then at 0, it's going to switch to a really high y coordinate, or a high derivative, which means it's going to look like that. The other thing we can do is we can look at the second derivative chart. Oops. We know that the second derivative equals the derivative of the first derivative. And what's another name for derivative? Slope. So we can look at the slope of the first derivative. Is that positive or negative slope there? Positive. Yep, that goes uphill. Positive slope on the first derivative means the second derivative is positive. Up until negative 3. At negative 3, there's no slope. There's a discontinuity, so f double prime would be undefined. From negative 3 to 0 goes this direction. So is that negative or positive slope?
Negative.
Negative. At 0, there's an asymptote. There's no slope, so the second derivative is undefined. How about to the right of 0? Is that negative or positive slope? Negative. So you look at this, and the question is are there any points of inflection on this original graph of f of x? Well, certainly not at 0, because the second derivative doesn't change signs. What does a negative second derivative tell us about the original function? Concave down. It's concave down here, and concave down here. So there's no switching concavity, so this cannot be a point of inflection. But here, we go from a positive second derivative to a negative second derivative. So it goes from concave up to concave down, concave up, concave down. So the question is, would that be a point of inflection? Now, the definition of a point of inflection says the concavity has to switch and a tangent line has to exist. If it's a corner like this, a tangent line would not exist. So this problem would have no, f of x has no points of inflection. Even though f double prime switches signs at x equal negative 3, a tangent line Doesn't exist at x equals negative 3. So, no point of inflection exists. %of the time, if you get a change in the second derivative, a point of inflection will exist. It's only because of this corner that it's not a point of inflection. It's a little bit of a trick question. Any questions about that?